In section 2.3, we're going to be looking at something called the chain rule. The chain rule is really good for functions that are basically more complicated. You've noticed that at this point, we've just kind of handled power rule and we've just kind of manipulated problems. We did get into product and quotient, but there's still some functions untouched that we cannot currently take the derivative of. And so what I want to do is I'm going to specifically look at this rule, and you're going to see the different options that we can work with it. So the chain rule can take the derivative of composite functions. And so when you're approaching the chain rule, what you want to remember is that you are going to work from the outside in. So you're going to work from the outside inward. And so what I want to do is I want to look at this first example, and I want to first look at it the old way. Let's look at it from a perspective that we already know how to handle it. So sometimes with doing derivative, we've talked about this, you do your algebra before you do your calculus. And so if you take this and you do your algebra first, this is 2x plus 3. When you square it, it's times 2x plus 3. Don't do any bad math there and distribute the square by any means. And so if I FOIL this out, this gives me f of x equal to, let's see, 4x squared plus 12x plus 9, just doing, distributing, combining like terms. So if I do my algebra first, great. And so now when I go into the next step and I take the derivative of it, I just apply that power rule. So I bring the 2 down. This gives me 8x plus 12. Hopefully at this point you're able to do some of these quick ones kind of in your head, and you're no longer pulling the 2 down, showing subtraction from 1. Now there's nothing wrong with that approach. We did our algebra and then we did our calculus. But let me show you how the chain rule is going to work. So when you're executing the chain rule, here's what you're going to do. So I'm just going to come over here to the side and let's apply our chain rule. And because we're doing the exact same problem, we should get the same answer. So first I'm going to start with the function. So I have f of x equal to 2x plus 3. And so what you do is you work from the outside in. So if this function had just been something raised to the square power, you would do the power rule. So I'm going to go ahead and say f prime of x is equal to, I'm going to bring this 2 out front, so that gives me 2 times this grouping, and subtract 1 from the exponent. And that's just executing your power rule on a variable, but we just happen to have a grouping here. Now we are not going to do anything to that 2x plus 3. When you're executing the chain rule, you just do one step at a time. Now here's the difference between chain rule and product rule. When I move into my next step, it's going to be multiplied. It's not going to be the addition of anything else. So first thing I did was I brought that 2 down, subtracted 1 from the exponent, and I left the inside the same. Now I'm working from the outside in. I'm going to address the inside part. The derivative of 2x plus 3 is 2. So that's my raw derivative using my chain rule. And so now I'm just going to clean it up. And so it gives me f prime of x equal to, let's see, 2 times 2 gives me a 4. 2x plus 3 is just to the first power, so I can now distribute this in, and this gives me an 8x plus 12. So you can see that whether I did my algebra first or my calculus first, because here is algebra first and then calculus. You can see over here I did my calculus first and then I did algebra to clean it up. But regardless of that, we still get the same answer. And so we talk about this being kind of the composition of two things, because if you consider f of x, this is like you had something squared, and that something you were plugging into your template was like a 2x plus 3. And so I think the best way we can kind of approach this is let's look at a couple more examples and just kind of work through some of the dynamics of this. Again, we're going to be working from the outside in using our power rule along with other rules. So let's look at this next example here. So what we want to do is, I in no way want to work that out to the 8th power. But what we're going to do is we're going to work on the outside in, And so I'm going to say f prime of x. It's important that your notation is correct because you can see in that first example, I stayed red. So that was doing algebra. And then it was like, look, person reading this paper, I have now switched over to the derivative. So I'm going to say, okay, I'm going to take this exponent. I'm going to bring it out front and subtract 1 from it. So that gives me 8. Leave your 2x plus 3 alone and subtract 1 from that exponent, which gives you 7. Then work your way to the inside and say, what is the derivative of this inside? And that's just a 2. You're going to multiply those results together and then clean up as much as you can. So in this case, I can multiply the 8 and 2 together to give me 16. And again, I am not going to take 2x plus 3 to the 7th power by any means. So that would be my final answer. So you can see how this chain rule is very beneficial because at this point, all we could do was apply algebra and take it to the 8th power, but that would be a lot of time and quite a few terms, whereas this is the more simpler answer as leaving that 2x plus 3 to the 7th power. Question number 3, it says f of x is equal to 1 over 2x plus 1. So just like we saw in previous lectures, you want to think about, okay, so let's kind of think over here to the side. If I have 1 over x, if I can move that x up to the top, that would give me x to the negative 1. And so we're going to use that rules of exponents to help us with this. We're going to take this bottom part and move it up to the top. And so that would give us 2x plus 1 to the negative 1 power. So that negative 1 power allows us to do our power rule as well as our chain rule. And so I'm going to say f prime of x is equal to, so I'm going to take that negative 1, I'm going to bring it out front, leave your grouping alone, subtract 1 from that negative 1, be careful with your negatives, that's a negative 2, times the derivative of the inside, which is just 2. That's my raw derivative, so now I need to use my algebra and clean that up, so it gives me a negative 2 on top. I'm going to move that back to the bottom, so it gives me 2x plus 1 squared. And again, I'm not going to square out that denominator. You're going to see a lot the denominators being left to a higher power. Now that we've kind of filtered through a few examples here, what I want to do is I want to move down here and let's write what we're doing with chain rule in very general terms. So if we are executing the chain rule, here's what we are doing. The chain rule says this, that if you are taking the derivative with respect to x of f of g of x, so a composition of functions, then the derivative would be f prime of g of x, so you take the derivative of the outside times the derivative of the inside. And so again, we're going to work through these quite a bit and do quite a few more examples. Now that's showing it through composition. If we wanted to treat that inner function like it was a singular term or a grouping like we saw, we could even say, what is the derivative with respect to x of u to the n? And that would be equal to bring the n down times u to the n minus 1 times u prime. And that's what we've been doing this whole time. We take that n, we bring it out front, we subtract 1 from it, and then we multiply it times the derivative of whatever's on the inside of that function. So again, this is going to be very beneficial for functions that algebra is very overwhelming, or also we're going to see it in some trig functions as we move forward, where that would be our only way that we could do it is using this chain rule. So let's just kind of continue with our examples here. Here's example number 4. It says y is equal to the square root of 3x squared minus x plus 1. And so to approach this problem, I do want to do some algebra before I get going. So over here to the side, let's think about this. And I want to say, remember, square root of x is equal to x to the 1/2. We've already seen that when we were executing or using our power rule. So the first thing I'm going to do is I'm going to write what I intend. I am going to rewrite this as 3x squared minus x plus 1 to the 1/2 power. That's going to help me to execute that power rule. Now I'm going to take the derivative of it, and I'm being very color-coded here because I'm wanting you to see when are we doing algebra and when are we doing derivative. And I'm wanting you also to note that Notice I am showing when I am switching to my derivative as I go out. So make sure your work is very clear and concise because that's what's going to deem you maximum credit on your exam. If it's all over the place, I do not work hard to read scratch work. It needs to be very formal. It needs to be very nice. Those are your small opportunities that I even look at your work. So that's why I expect them to be well done, because I am not checking homework notation throughout. But I'll be happy to check that if you need assistance. So I'm going to do my power rule here. So I'm going to take that 1/2 and I'm going to pull it out front. So I have 1/2 times, leave all this grouping alone, subtract 1 from that 1/2, be careful, that's a negative 1/2, times, now I'm going to take the derivative of that inside. So that would deem me 6x minus 1. And that is my raw derivative. Now we're not done there. You always have to clean it up. So make sure you fully simplify, again, for full credit on your exam. So to clean this up, I'm going to go ahead and approach this like it's a fraction, because I already see that I'm going to have a negative exponent. I've got a fraction out here. So I drew my big fraction bar, 1/2. I'm going to go ahead and put that 2 on bottom. 6x minus 1 is going to remain on top because it does just have a positive 1 exponent. And then I'm going to go ahead and move that grouping of 1/2 down to the bottom so that I can now make it a positive exponent. Going back to algebra, that's where you always finish up problems. You never leave negative exponents. And then I always say, put the problem back in the form that it was given to you as. And so since it was given with a square root, finish it out as a square root. And again, be careful, because the downfall of the online homework is it is very accepting of things, but it is not real world of, oh, you could just leave a raw derivative. You have to clean things up and get them to a better point. And the reason we want to clean things up as much as possible, and you're going to see this as we move forward, is sometimes we're going to take that result and we're going to do more with it. So it's making our life easier for harder problems that we're going to face. Let's look at this trig problem here. So when we're facing with trig, you're going to treat it the same way. You're going to work from the outside in. And so I'm going to say y prime is equal to, outside would be the sine function. So what is the derivative of sine? That would be cosine of 2x. And so you're going to leave the 2x alone. But since I'm taking a trig function of a grouping here, or another function, I also have to remember to take the derivative of 2x. The derivative of 2x is 2. Now the cleanup for this is to rewrite it with the 2 out front, because if you leave the 2 in the back, you might be tempted to put these two together, and we cannot. We are doing cosine of the 2x, and then we're multiplying that result by 2. So be very careful with how you're doing that, that you don't overwork the problem or simplify where you're not able to. And so that would be my final result. Let's look at tangent. Now, when we're looking at tangent, you're going to notice that when you have a squared of a trig function, they're going to put the little squared right here. In results of doing our derivative, it is more user-friendly for us to rewrite as the whole thing squared so that we can apply our power rule correctly and do our chain rule correctly. But just know, this is the proper formatting for finishing up a square of a function. It's emphasizing that the tangent is being squared, not the x. And we're going to see this in some other examples as well. And so the first thing I did was I used my algebra and I rewrote it. And then my derivative is going to be equal to, bring the 2 down, subtract 1 from it, times the derivative of the inside, and the derivative of your tangent is secant squared. Make sure you know all 6 trig functions and the derivatives. That will not be given to you in any kind of formulas or notes, but hopefully the repetition of working with them, you're learning those along the way. Now, really the only cleanup that we can do is just a formatting thing. So we could say 2 tangent x secant squared x. There's really no need to put that large groupings around the tangent or the secant squared. And then you'll also note too that tangent x first or secant squared x first is irrelevant because multiplication is commutative. And so that would be my final answer. Let's keep moving forward and let's look at example 7. Example 7 says f of x is equal to the parentheses x squared plus 1 to the 3rd power. So we're going to execute our chain rule here. And so I'm going to say f prime of x is equal to So I'm going to take this 3 and I'm going to bring it out front. So 3 parentheses x squared plus 1 to the second power times the derivative of the inside, which is just 2x. Again, clean that up as much as possible. So I'm going to put that 3 and 2x together. And so that gives me 6x parentheses x squared plus 1 squared. Don't overwork that. Just leave it right there. Getting the hang of this? Hope it's going well. Look at f of x equal to 3x minus 2x squared to the third power. Again, we're going to execute chain rule, so we're going to work from the outside in. So I'm going to take this 3, I'm going to bring it out front. This gives me f prime of x is equal to 3x minus 2x squared to the second power times the derivative of the inside, which is 3 minus 4x. And then clean that up. So I'm going to do the 3. I'm going to go ahead and distribute it into this grouping because this one's being blocked by the squared. So it gives me 9 minus 12x times 3x minus 2x squared squared. And that would be my final result. So you can see this chain rule is becoming super handy for us. Now what I want to do is I want to take that chain rule and I want to combine it together with some other rules that we know. So let's look at this one. We have x squared times the square root of 1 minus x squared. And so what I want to do is notice what two rules are we going to use? Well, I can see that I have a function times another function. So we're going to have to execute a product rule. And so when I do derivative of the first times the second plus the first times the derivative of the second, when I get into this second function here, then I'm going to have to execute chain rule throughout it. So my best advice for you as you're moving forward and doing these harder problems is to go slow, be detail oriented, and think through what kind of derivatives you're going to have to do. So let's see what we can do with this. And so I'm going to say h prime of x is equal to, so I'm going to do product rule, derivative of the first, so the derivative of x squared is 2x, times the second, square root of 1 minus x squared, plus the first, so leave x squared alone, times the derivative of the second, so we're going to have to work with this piece right here. Now you can see what we should have done to start with is some algebra, because that's an x squared, and I should have written this as 1 minus x squared to the 1/2. So that when I get to this next step of doing the chain rule on this function, I can bring the 1/2 down, times, leave the inside alone, subtract 1 from the exponent, times the derivative of the inside, negative 2x. Don't forget that negative. So let me go ahead and manipulate this first one here, just so we're working with all the same pieces. And again, that would be that 1 minus x squared to the 1/2. Now, that is my raw derivative. Algebra is what's going to get you. I feel like a broken record. I keep telling you, algebra is what's going to get you. And it is, because now we're going to clean this up and you're going to have to remember two rules. You're going to have to remember how to factor, and you're going to have to remember your exponent rules as we go throughout. So if you look at this grouping, I have essentially two pieces. I have this piece here, and I have this piece here. And when you look at these two pieces and you want to think about factoring, you're trying to factor out everything that they have in common. And so maybe let's clean up the next step before we begin to factor. So this would be h prime of x is equal to, I can't do much to the front, but on the back side, let's see, I can put my x's together. I've got an x squared and an x, so I have an x cubed. This 1/2 and negative 2 just gives me a negative 1. So let me just change this sign here. And then I have this grouping 1 minus x squared to the negative 1/2. I'm just going to put negative. 1 doesn't matter. So if I look at this grouping here, I've got this big group, and this back one looks a little bit better for us to handle. Okay. Now, when you think about factoring, you are pulling out everything they have in common. So let's first look at coefficients, or the large numbers. They don't have any large numbers in common. We've got a 2, we've got a -1. So I move on to the next piece. They both do have an x, and when you're looking at variables or grouping, you take the smaller of the exponents. And so just a regular x being brought out front would be the smaller of the two exponents. Then I'm going to look at the next piece, and I can see that they both have this grouping of 1 minus x squared. And so again, factoring out, you take the smaller of the two exponents. The smaller of the two exponents is going to be 1 minus x squared, -1/2. Don't let those negatives fool you. So now think about your algebra. If I am taking out the least exponent, or taking out that -1/2, I am going to do 1/2 minus -1/2 to just leave the grouping. 2, we took out the x, just leaving the grouping of 1 minus x squared. Then I'm going to look at the next piece, so that would be minus. I have an x cubed, I'm pulling an x out, so it leaves me with x squared. And then I took this whole piece out because I'm pulling that whole grouping to the -1/2 out. So this would be my final result. I know that caused a little stress. You lost your breath for a minute. The whole reason I want to do that is because look how nice this grouping has become. Let's do some algebra and clean that up. So I'm going to distribute this 2 in here. So we've got x times 1 minus x squared to the -1/2. So it gives me 2 minus 2x squared minus x squared. I can put these two terms together. Just bringing this first part down. So it gives me 2 minus 3x squared. And then, as we stated in other problems, we want to make sure we don't leave any negative exponents. And so this leaves me with x, 2 minus 3x squared, all over, move that back on bottom, 1 minus x squared to the 1/2, but let's go ahead and put that square root back on it. Oh, goodness. So look at where we have come from. We started here with this raw derivative, and we have now arrived here at this fractional function here. The whole reason, again, we want to do this cleanup is because if we are not cleaning it up to get to this point, when we go into multiple derivatives or doing something else with it, we're not going to be able to manipulate it or do the things that we need to with it. Okay, let's go into another example, and I'm trying to work a little bit harder examples for you so they're not as overwhelming. Let's look at the derivative of a quotient that also involves that chain rule. Now, if you didn't like quotient rule, like that really wasn't your favorite rule, you could come up here to the side and you could say, you know what, this is equal to, let me go ahead and get rid of that rational before we get to work. So this would be x squared, or radical, excuse me, x squared plus 4 to the 1/3. You could come up here and you could say, you know, I'm just going to bring that up, and that gives me x times x squared plus 4 to the -1/3, and then you're back to the previous problem. But what fun would that be, just doing product rule again? And so you can do product rule on this. You show your work, you're going to get full credit. You are correct. You are mathematically correct, and that's the main thing I want you to be. But I want to do this example, and I want to approach it with quotient rule, because I want you to see how that's going to work out, because maybe that's a little bit quicker, or maybe you didn't see product rule like I did. So I want to make sure you have some good tools in your tool belt as you approach other functions. And so I'm going to take h of x equal to x over x squared plus 4 to the 1/3. Now I am going to leave it as that 1/3 and not the cube root, so I can execute my chain rule and power rule. All right, so now when we take that quotient rule, we are going to say h prime of x is equal to derivative of the top times the bottom minus the top times the derivative of the bottom. There's your chain rule. So I'm going to bring that 1/3 down, leave the inside alone. Oops, excuse me, skip down a little bit. And then I'm going to subtract 1 from 1/3. So be careful, that's -2/3. It's those fractions and negatives that are going to really get you when moving your exponent down. Times the derivative of the inside, x squared plus 4 is 2x. All over the bottom, x squared plus 4 to the 1/3 squared. and that is our raw derivative. So now it's time for the cleanup, probably your favorite part. And so first thing I'm going to do is I'm going to clean up that numerator, and that gives me h prime of x is equal to x squared plus 4 to the 1/3 minus, let's clean up that. So let's see, coefficient wise, I've got a 1/3 and a 2, so it gives me 2/3. Let's see, x and x, so I've got an x squared, and then that grouping x squared plus 4 to the negative 2/3. All over on the bottom, 1/3 squared is going to give me x squared plus 4 to the 2/3. All right, so it's looking a little bit better. Now when we look at this, if we do it like we did before and we look at what is the part we could factor, or what do they have in common, you can see that they both have these groupings in common. And so I'm going to pull the smallest of that grouping out front. And so that gives me x squared plus 4. The smallest exponent is negative 2/3. When you pull that out, taking a 1/3 minus negative 2/3 leaves you with an x squared plus 4 minus 2/3 x squared, and we took that whole grouping on that back one, all over x squared plus 4 to the 2/3. Now that I have it factored, the benefit of doing that factoring is the fact of I can now move this piece to the bottom because I'm looking at multiplication. Moving up here. So let's see, on the bottom, that's going to give us an x squared plus 4. So a 2/3, moving this positive 2/3 down, adding them together gives you 4/3. And then on top, I have an x squared and a negative 2/3 x squared, which gives me a positive 1/3 x squared plus 4. And then you never leave fractions within fractions. And so what I can do now is I can get rid of this 3. So in order to do that, I am going to multiply by 3 on top and bottom. This is just a big old fancy 1. So I'm not changing the value of the problem any. What happens in the top is you get a positive x squared plus 12. All over, now you have the 3 in the bottom, so it's an x squared plus 4 to the 4/3. Now don't be hasty and just move this down, because you can see that this 4 has now changed to a 12 in the moving of that 3 down. And then this is your final result. And yes, if given a problem like this on the test, which I do like to include one that has the moving out of that negative fraction like you've seen in the past 2 examples, this is the full work that I would need to see. Now we've only done a couple trig problems, so to kind of continue this lesson, I want to look at some more trig. So let's look at applying the chain rule to trig functions. Now this first one's a little bit different, and I have a little typo here. Let me put a little 3 right there. This is sine cubed 2x. And so the first thing I want to do is I want to do my algebra. We always see the little exponent right here between our trig function and the grouping, but algebraically, if we write this as sine of 2x and just reformat it to the 3rd power, that helps us execute our chain rule, again, like we saw earlier. So now when I come down here and I say y prime is equal to, I'm going to take this exponent and move it out front, 3 parentheses sine of 2x squared. Now I have to do the derivative of sine 2x. So again, you're working from the outside in. The derivative of sine is cosine of 2x. Leave that 2x alone. Now we're working to the inside of it, and the derivative of 2x is 2. Whew. So we moved the 3, then we did the sine, and then we did the 2x. Now you got to clean it up. So I'm going to put this 3 and 2 together, so it gives me a 6. I'm going to go ahead and move that cosine 2x in front, and then I'm going to revert back to sine squared 2x, the better formatting of those trig functions. So you can see that one was definitely not as intense as other problems, but you go back to our basics, work from the outside in. Let's do another one. This one I wanted to look at. I want to look at 2 examples because parentheses matter. You can see that in the first function, I am doing the cosine of 3x squared. And the second function, I am doing cosine of 3x and then squaring the 3x. Your exponent only applies to what it's touching. And so if I had one more example here, you can see that this squared is touching the cosine, so that's what it was squaring, and that's why we have written cosine of 3x squared. And the second one, you can see that the squared is only touching the x, so that's all it's squaring. And the third one, you can see that in 3x, the squared is touching this whole grouping, and so that means 3x times 3x. And so make sure you're aware of those three situations. I've got this third one typed down here. And so again, that squared, just the placement of parentheses plays a big deal. So let's work through these. The first one, if I was doing y prime, that would be equal to, well, the derivative of cosine is negative sine, and then I'm going to leave that 3x squared alone, times the derivative of the inside, which would be times 6x. Now the best formatting for this is to have the negative 6x out front. Again, because of placement, you don't think that you're going to multiply it within here. That's a no-no. We're going to assign it first. So typically we like to put the multiplication out front of the trig function so you don't accidentally multiply it inward when you're not supposed to or can't. Now the next one is the squared on the 3x. So really what's going to benefit me here is to do my algebra first, and let's call that y equal to cosine of 9x squared. And then when I go to take the derivative of that, I'll just say y prime is equal to negative sine of 9x squared times the derivative of the inside, which is 18x, and then clean it up. So that would give me negative 18x sine 9x squared. And so you can see this result and this result were definitely different. I mean, it has some pieces in common, but you can see just the placement of those parentheses were different. Let's work this last one out. And so if I say y prime is equal to, remember algebra first with that sign, with this symbol here. And so that would be cosine of 3x, and that would be squared. And so my derivative would be 2, bringing it down, cosine of 3x to the first, times the derivative of the inside, which is negative sine of 3x, times the derivative of this inside, 3. So the cleanup on that would be negative 6, putting this 2, this negative, and 3 together, cosine 3x, sine 3x. And so again, you can see that this result is different than our previous two. So just make sure that you are detail conscientious, you seek help when you need it, and you're not overworking the problem, taking it step by step. But again, chain rule is going to benefit us as we move forward.